In the previous video, we introduced the idea of reaction progression graphs or reaction coordinates. So the idea with these is it shows the energy of reactants, the energy of products, and the progression of energy as the reaction proceeds from reactants to products. And what we established is that you always have to proceed through a high energy transition state, and reaching this transition state often takes a lot of energy. And just to kind of demonstrate how much energy we're talking about here, let's go ahead and estimate these energies by figuring out bond enthalpies. Okay, so if you look at a table of bond enthalpies, which you'll find in any general chemistry textbook, we can look up the bond enthalpy of an HH bond is 435 kilojoules per mole. This means it requires 435 kilojoules per mole of energy to break a hydrogen-hydrogen bond. Okay? Likewise, we can look up the bond energy, the bond enthalpy for chlorine, and this is 243 kilojoules per mole. Right? So these are both endothermic. It requires energy to break these bonds, and breaking these bonds correspond to this activation energy. Right? So this energy right here. The bond energy for a hydrogen-chlorine bond is 431 kilojoules per mole. Okay, so this means that to break an HCl bond, it requires 431 kilojoules per mole. But in this reaction, we're actually creating a covalent bond between hydrogen and chlorine. So in this case, this value for us would actually be negative. Okay, so let's apply Hess's law and figure out whether this reaction is endothermic or exothermic. So in our very first step, we have H2 plus Cl2, and we first want to convert this to 2 hydrogen atoms plus 2 chlorine atoms. So the energy that it requires for this reaction to happen is the sum of the bond energy of HH and Cl-Cl bonds. So this bond energy is going to be 435 plus 243 kilojoules per mole. So overall, this gives us 678 kilojoules per mole. So this would actually be our activation energy. This is the amount of energy it takes for the reaction to actually occur. There needs to be 678 kilojoules per mole of energy around if this reaction has a chance to happen. Okay? The next step here now is taking these 2 hydrogen and these 2 chlorine atoms and forming our new bond between the hydrogens and the chlorines. Right? And as we said, an HCl bond has a bond enthalpy of 431 kilojoules per mole. We have 2 of them, and we're creating a bond, so it's minus 431. So in this case, we have an overall negative 862 kilojoules per mole. Right? So, and as you learned previously, you can add up these chemical reactions. So what we see here is the 2 hydrogens cancel, the 2 chlorines cancel. So overall, we have a reaction of H2 plus Cl2 becoming 2 HCl molecules. And if you'll remember, this is exactly the reaction that we started off wanting to understand. Okay? So in this case, our overall enthalpy of a reaction is adding up 678 and negative 862, giving us negative 184 kilojoules per mole. Right? So this reaction is actually exothermic. Heat is released when this reaction happens. Okay? But what I really want to stress for this part of the class, for understanding this reaction, is that even though the reaction ultimately produces heat, it takes energy for this reaction to happen, right? So there has to be energy around. You have to make an investment for the reaction to actually occur. And if there's not this energy around, then the reaction simply cannot happen. Right? So the take-home message from this video is that the energy that it takes for a chemical reaction to occur is known as the activation energy. And for some reactions, this energy is really, really big, and that dramatically limits how likely it is for a reaction to happen. Some reactions, however, have really small activation energies. Right? So this would be a small activation energy, and if you have a much smaller activation energy, then it means the reaction has a much better chance of happening because the amount of energy you need, the investment, is much smaller. Okay? This particular reaction has a very large activation energy, and it's hard to happen. So what we're ultimately working towards here is thinking about steps that we can take to make these chemical reactions more likely by decreasing the activation energy. In the next video, we're going to introduce a common chemical reaction and explore how the functional groups in that chemical reaction make the activation energy much smaller than what we would originally predict, therefore making the reaction much easier.